chatbots sit idle, waiting for a user prompt to generate text. Agentic AI operates differently. These systems perceive their environment, reason through complex workflows, and execute autonomous actions across multiple applications simultaneously. Looking at early AI infrastructure, developers faced an integration nightmare known as the M by N problem. Every different language model required a custom-built connector for every single external data source it needed to access. This hard-coded fragmentation meant enterprise AI couldn't scale. Building and maintaining unique pipelines for every API, local file, and database was too fragile and resource-intensive. The architectural solution to this bottleneck is the Model Context Protocol, or MCP. It replaces the tangled web with a single universal routing help. Think of MCP as the USB-C standard for artificial intelligence. It provides a universal connective tissue that links any probabilistic language model to any deterministic tool without requiring vendor-specific adapters. Decoupling context from execution solves the interoperability problem, but it also shifts the model's role. It is no longer just predicting the next word in a chat. It is now an active agent, capable of interpreting data to trigger commands across a connected ecosystem. In traditional software architecture, security is a distinct discipline. It focuses on defending a perimeter against malicious external adversaries trying to breach the system. Software safety deals with internal stability. It ensures the code operates as intended, preventing crashes, race conditions, or operational bugs. The Model Context Protocol ecosystem forces these two domains to collapse into one another. In an agentic environment, the boundary between a safety bug and a security breach disappears. An epistemic safety failure, like a model hallucinating a set of instructions, can immediately trigger an unauthorized action. An AI mistakenly deciding to delete a database or exfiltrate sensitive data to a public log becomes a critical security event. Because incorrect text output now leads to operational outcomes, the security challenge changes. Traditional firewalls, which monitor network traffic and code signatures, cannot see or stop a model that is honestly following a set of malicious instructions found in its context. This diagram compares traditional API routing with the MCP standard. On the left, a standard REST architecture relies on a stateless, linear data request, moving directly from a developer to an API gateway. Here, execution paths are hard-coded and predictable. On the right, MCP operates differently. An LLM interface processes intent-driven sessions, creating branching paths based on context. This transport layer uses standard input-output pipelines or server-sent events. Within this environment, there is no hard-coded developer path. The language model itself dynamically decides which tools to trigger based purely on its semantic understanding. Control flow is driven by non-deterministic logic instead of predictable code. A traditional perimeter security tool cannot inspect a JSON RPC message and validate the semantic safety of the action the model intends to take. Looking closer at the data flow of an MCP request, the protocol operates across three distinct blocks: the model interface, the MCP client, and the context source. The sequence begins when the model interface processes contextual data, deciding to utilize an external tool. It serializes that command into a JSON RPC packet and pushes it into the middle MCP client block. The host application managing this client acts as the central policy enforcement layer. Before execution, the request must pass through a strict host policy or human approval check. In a decentralized multi-agent system, this localized host-mediated approval loop serves as the only definitive line of defense, preventing an automated full system compromise. Connectors expose their data to the MCP ecosystem using three specific protocol primitives. First, the resource, a passive data stream. Second, the prompt, a prepackaged template. Third, the tool, an active capability. Attackers exploit this through context poisoning. Malicious data injected into a resource corrupts the model, which then automatically triggers an unauthorized tool execution. Now that the language model has the power to trigger active tools, it essentially operates with dangerous shell-level privileges. Manipulating its passive read-only context is functionally identical to achieving direct remote code execution. These vulnerabilities extend beyond enterprise servers. Microsoft Recall takes continuous screenshots, building a searchable database of every message, website, and file on the machine. To secure this data, The runtime architecture relies on an active AI host process, reading from a locked, encrypted SQLite database. But the access control model is deeply flawed. It requires biometric authentication during initial setup, but removes it for runtime access. An attacker can bypass the biometric lock entirely using just a basic 4-digit PIN. In minutes, a non-technical user can search and extract highly sensitive context, including visual classifications, credit card numbers, and even auto-deleted messages. Applying heavy encryption to a local database means nothing if the access control model fails to continuously verify identity and intent at runtime. Traditional one-off quality assurance testing cannot secure these environments. Non-deterministic agents require ongoing cyclical validation. The solution is Unified Data-Driven Testing, or UDDT. This framework implements a continuous feedback loop where structured datasets constantly probe the agent's behavior. By benchmarking performance against crafted adversarial inputs, teams measure the robustness of the agent's guardrails. When anomalies occur, an automated filter classifies the risk score, routing flagged outputs to a subject matter expert for validation. In production, testing must be paired with strict runtime defense. Agent activity must run within isolated kernel-level session containers, completely severed from external operating system processes. Organizations must enforce strict process-based access controls. Deployed agents must be structurally incapable of modifying their own logic or expanding their toolsets without a forced manual republishing cycle. As the tech industry transitions toward autonomous agentic operating systems, AI can no longer be treated as unmanaged automation. It must be governed as a highly privileged, tightly auditable application, because in the MCP era, the boundary between an innocent hallucination and a catastrophic system compromise has ceased to exist.